I introduce Phil, W1PJE.
Hi, folks.
Talking about HamSci.
All right. All right, let's see if I can push the right buttons here. They're not supposed to let the science people at the equipment. Okay. Does that look okay? Yeah. Whoa. Yeah, that works. That works. Can you do the middle? Yeah, that'll work great. Yeah, perfect. Okay, and Jim, you want me where? About here?
Yeah, right.
Does that work?
Fine. You can go another foot to your right.
Okay. Yeah.
Yeah,
All right. So tonight I'm going to try to give you a little update on HamSci, and I realize that we have some new hams in here, as well as people, a lot of friends that I have known for a bit now, and so I'm going to try to see if I can. I've tried to set the level here so that people hopefully can follow along. And we'll see how that goes. So I'm Phil, for those who don't know me. My call sign is W1PJE, and I'm the director at Haystack Observatory, which is it's the intersection of Groton, Westford, and Kingsborough. It's about 20 minutes, that way, along Route 40. And what I'm going to present tonight has heavily borrowed from my colleague Nathaniel Frizzell. Nathaniel is a professor at the University of Scranton in Pennsylvania, and he's a colleague in my field, and he's actually been the person that kind of put HamSci together. And I'll be telling you a little bit about some of its history, but also kind of what people have been up to right now. And I've tried to tie us to NVARC at some points in this talk. But what I want to start with is the fact, so I took that in my office earlier today. The coffee cup on the upper left-hand side is all Skip's fault, because Skip invited me to give a talk 2014, somewhere in that range?
Doesn't matter.
Something like that. And I did not have a license at that point. I started out life as a shortwave listener and then kind of get involved in rather large transmitters, and so didn't necessarily feel as much of the urge to run a transmitter myself at home, and Skip corrected that problem. I do still give that cup to visitors who need a cup of coffee, so it's one of the little stable I have. And honestly, the other stuff there, for anybody that's interested, the upper right-hand corner is the 140-foot antenna at Green Bank Observatory. That actually is the largest equatorial mount telescope in the world. It is not azimuth and elevation, it is right ascension and declination. They've never built an antenna like that again, and they will never build another antenna like that again. There's a whole story behind that. The bottom is something that I was involved with. I got to author a couple hundred pages of that. That's called the Decadal Survey. Our field every 10 years gets together and tries to figure out where things are going in the next 10 years. And then the other thing is, if you really can't sleep, you can read Budden's Propagation of Radio Waves, which is 500 pages of equations. But my point is that NVARC has actually been an absolutely wonderful key for me to the whole world, not only of amateur radio, but also to a lot of professional connections, which have proved very, very fruitful, and I hope to go over some of those today. So I thank all my friends here, especially Skip, especially Bruce, and the other folks here whom I've known for a number of years now. It's been a real delight to be able to correct my mistake for not getting licensed until Skip dragged me here. So thank you, okay? I really do appreciate that. All right, so HamSci, what is that? This happens to be the homepage of HamSci. It's a citizen science project, and citizen science has become a growing thing in terms of connecting people like everybody in this room who are interested people but are not necessarily professional radio science people or atmospheric physics people, and actually sort of get the community together and then try to do useful science in a way that is not really replicated by those professional radio science remote sensing networks that we have. And it has gotten now to the point where it is an official NASA citizen science project with some funding. So far, Nathaniel's leadership, along with a bunch of other people, sometimes me, that help write grants, we've managed to generate $6.2 million since 2019 in federally competed grants to do this kind of research. It has been really successful. We have connections also to ARDC. If anybody doesn't know what ARDC is, that's the Amateur Radio Digital Communications. They give out grants. The largest grant they gave out was about $2 or $3 million to MIT to refurbish the 5-meter antenna on top of the Green Building. Next time you're on Mem Drive, look up and you'll see a radome up there. That was refurbished by ARDC. ARDC, by the way, has an enormous endowment because they bought the 44 net of the IPv4 range in the very early days of the internet, and they sold it for 8 figures. A portion of it, not even the whole thing. And that funded this perpetual sort of grant mechanism. So we're tied off to that. The YASME Foundation is something that Ward Silver, N0AX, whom you may know is the author of the ARRL handbook for quite a while, is a principal in. That's the Frankfurt Radio Club in Pennsylvania, and then I mentioned NASA and the National Science Foundation. So it's really developed into something that has a lot of parallel tracks, as I think you'll hopefully see. If you go to the HamSci website, which is hamsci.org, pretty easy to remember, there are some very, very nice newsletters, for example, where you can kind of get an overview of what's going on. That's the spring 2026 one. And on the right-hand side, not that you can read it, but that's a screenshot of the Google Groups listserv, which you can sign up for, where you'll see traffic now and again on what HamSci is doing, what's going on at a particular workshop that's coming up, what kind of projects are going on. This is very active and anybody can join, so that's one thing you can do. Another thing you can do is participate in a workshop. This year, for the first time, and I did promote this, I believe, in the NVARC newsletter, this workshop was in driving distance from here because it was at Central Connecticut State University, which is literally 10 minutes or less from ARRL headquarters in Newington, Connecticut. That was in March, mid-March, 2-day workshop on a Friday and a Saturday. There's the collective, group photo. Can you find the NVARC members?
I found one.
You found one, okay. I think there's 2 here. I'm hiding back here, hiding. But you'll notice somebody else that you...
Bob's in there.
Exactly. Bob Reif is in there. Bob is smiling faces right over here. And there may be other ones, but I know that those 2 people are in there. So this is a workshop that's now held every year. And it's an interesting combination of technical talks and also sort of students showing off what they're doing. And for example, this is the poster hall. There's a whole poster hall. I'm standing there with my back to the camera, and my colleague Jim LaBelle, who's a professor at Dartmouth, drove down to HamSci. He hadn't really been to the workshop before. So we had a lot of activity at the poster hall. But today I discovered that I don't even have to start putting up pictures. The ARRL did a very nice job at providing a 2-minute overview. So we're going to just try that. And let's see. Well, there's a little music, but just watch. I'll step over here. My colleague Hyeolmin Kim, professor at NJIT. Another person describing a technical project. There's the poster hall. Students. My colleague from Haystack who drove down. Someone testing a magnetometer and a magnefield coil. Looking at oscilloscopes. There's a person, somebody does NASA science. Chatting with a few of my friends. There's there were main talks. These are 2 very impressive young people who were doing a project. That's Nathaniel himself, the HamSci lead. And then we got to take a field tour to ARRL headquarters, which was very nice. So this is inside headquarters. That's the headquarters hall. This is the laboratory, the testing laboratory. There's W1DRF showing us that. That is Steve Goodgame, who's the ARRL Teachers Initiative, talking about his classroom work. And this is the station manager for W1AW, Joe Sciarcia. Forget what Joe's call is. And there's Bob Inderbidson, who is another ARRL employee, talking about that. So you can see kind of the breadth of activities, and this is just the workshop. So quite enjoyable, quite extensive. The workshop rotates around. I don't really know where it's going to be next year, but if it happens to be within your means, I would highly recommend that you check it out. So, oh no, I don't want to do that again. This is just a screenshot from 2 of the 5 oral sessions with talks over the 2 days, and then there were 32 posters that were available in the poster session. All the talks are online. I understand that, I say all, not all of them, but eventually, in a little bit, all of them end up on YouTube. That's the program link. If you wish to look at it, I'm going to leave the slides with Jim so that you can have these links. So in addition to having its own dedicated workshop, HamSci does show up at other particular things, like this is Hamcation down in Florida. That's Gary AF8A, who has been doing a lot of media coordination. Spot the NVARC member on the right-hand side. There's Bob again, W1XP, along with my colleague Bill Angelke at the University of Alabama. There's Gary again, and that's Ed, WX2R, who is actually one of the ARRL public relations people, who has been helping a lot with things like the newsletter. So that was Hamcation this year. And then we had Hamvention, and Bruce was talking about presentations. That's the booth area, and can you spot the NVARC member again in the right-hand side? If you answered correctly, there he is again. Bob's been very active in something called the GRAPE project, which I'll talk about in a moment. So what I can tell you is that NVARC is quite well represented in this particular collective. So I think the club should all be quite proud of that. So what do we study? And again, because this is a large group, I thought I'd give you just a little bit of background. Don't worry, this is not a 15-minute AGU science talk, okay? Because I know that somebody would accuse me of that. And in fact, if you don't pay attention to me at all, you can find about a 300-page book that talks about the Sun-Earth system as a user's guide with like numbers that are related to real life. This is a guy named Jack Eddy, who is no longer with us. It's a 29 megabyte PDF textbook. For some reason, NASA took it down, but if you follow the archive.org, you can download this whole textbook. It's a great reference to space weather and what's going on in the system, part of what HamSci studies. If you want a book that's actually more tuned to what we do in the hobby, this is the Little Pistol's Guide to HF Propagation. So for those of you who are new, if you get on the HF bands, as we'll see, waves don't go in straight lines, they begin to refract. And this is Rob Brown, NM7M, who was a professor at Stanford for quite a number of years. And thanks to my friend Carl K9LA and his family, all of the books, several of them are available free in PDF form on Carl's website. You could also look at propagation chapters in the ARRL handbook and the ARRL antenna book. And there's even the CQ shortwave propagation handbook. That was in 2021. So leaving you these references because there's a bunch of things where if you don't remember what I said, at least you could look it up. The ARRL even put out a dedicated book in 2023 that focuses on radio wave propagation, and I believe this is Kindle friendly, so if you want to download that, you can do that. There's, for example, most of the topics on there. So now you can forget everything I'm going to say in the last little bit because you can look it up, okay? But let's put this in your short-term memory. This is my colleague John Schoenberg, NT1D, who is an engineer at Lincoln Laboratory, who provided me kindly these things. For radio wave, we have a couple of different propagation modes. For example, at UHF, it's direct wave line of sight. So you're going to get between 15 and 50 miles before things like trees and the horizon get in your way. And that's, of course, affected by how high your antenna is, what the gain is, what the transmitter power is, how sensitive your receiver is, what the terrain is, and who else is screaming away in the band when you're trying to transmit. The nice thing about HF, and we're going to be talking about HF a bit here today, is that the ionosphere, it provides this very nice reflection height, which of course is how we all enjoy HF in this hobby, which will go quite a bit beyond just the line of sight to the horizon. And you can, in fact, if you have a single hop, you can get up to about 2,500 miles if you have an antenna at low elevation, and then sometimes it will hop again, as we'll see. And that depends on a lot of variables, including some that have to do with the state of the upper atmosphere above our heads. And so this is where sort of HamSci begins to wiggle in terms of extracting some information from people making contacts. And understand, why does these contacts work at certain times of the day and other times not? So this kind of, again, just as a summary, all comes from the fact that we have a sun, and the sun is the star we're living with, and it has radiation in a number of wavelengths, both very short and very long. And specifically at extreme ultraviolet, which fortunately doesn't get through the atmosphere because it'd be hard to live on the ground, those little photons pack enough of a punch that they can get down into the atmosphere and ionize it. They can strip off an electron and leave behind a positive ion, and so you get this thing called an electron density profile, which are just free charges floating around that eventually maybe recombine or get created again, and they change from day to night. There's still an ionosphere in the middle of the night because although the sun turns off, a lot of the chemistry keeps those electrons from recombining for several hours, and then some of them actually move from where it's sunlit on the planet to where it's not. So there's a lot of very interesting physics because we're living on a planet with an atmosphere that can be ionized from this radiation. And this is skywave, and as we all know, if you in fact start in this hobby by saying, okay, I'm going to get on the radio, and oh gee, 10 or 15 meters works pretty well during the day, and then at night it doesn't seem to work that well anymore, and things shift to lower frequencies, and then when the sun comes up they might shift to higher frequencies. That's all the ionosphere, the charged part of the upper atmosphere above your head, which is varying all over the place. Time of day, time of year, where you're located on the planet, even long-term, 11-year solar cycle or longer than that. And then there's background climate, and then there's variations. And after more than a century, we're still trying to understand some of the fundamentals of how that stuff varies. But one thing to leave you with is there's something called the critical frequency, or FOF2. That is, if I launch a wave with an antenna that mostly looks straight up, what frequency at HF is that wave going to end up sort of reflecting off the ionosphere? That's because when the wave gets to something that's related to the electron density frequency, it will turn around. That's called the FOF2. Conversely, if you're transmitting kind of at an angle, at a low angle, you can end up with a reflection, but the frequency can be very much higher than the local frequency, maybe by a factor of 4 or 5, just due to the fact that the wave is kind of bending at a low angle. And that's good for us because if it was always just the frequency for straight up, a lot of frequencies would not be terribly well, it would not go terribly well between continents. But this, as we'll see, this maximum usable frequency is something that actually makes HF very interesting, for example. It also means that there's a variation in this from day to night. Some countries are more easily accessed than others, but you never know. So, this is just another sort of, schematic diagram. This is the stuff that it really just goes straight up and reflects back. This is some of the stuff that's going out at lower angles and refracting or bending over. So if anybody is curious, this is a map of the FOF2. This is the frequency if your antenna is only going straight up, at which you're going to get a hard reflection. Above this frequency, stuff's going to go through and you're not going to get a reflection back. That's a global map from my friend Andrew Rodlin, KC2G, who does that in near real time. You can find that on his website. There's another talk about what data goes into that. But the maximum is about 15 megahertz in this particular plot. And this was back in February, and that would change, for example, if it was today. And you can kind of see the blue is lower frequency, and the yellow is higher frequency. And you can kind of see, where is it noon? Well, it's about noon here. Where is it the middle of the night? It's about the middle of the night right there. That's for waves that just go straight up and down locally. Anybody hear of near vertical incidence skywave, NVIS? That's that antenna mostly radiates straight up. Well, that's sort of the maximum frequency that antenna would see a reflection. This is the map for the lower angle maximum usable frequency. Now we're up to 47 megahertz. This is why, for example, a 10-meter reflection signal during the day will go a lot longer than you would expect just from looking at the local frequency above your head. Again, lots of variation in here. This is very, very smoothed. So this is why, you know, Bruce might turn on the radio and suddenly discover that he's talking to someplace, and a half an hour later, it's not there, because the ionosphere has changed some of these propagation modes. So this is just something to remember. And we have an atmosphere. Yay, we have an atmosphere. This is good. We're not living on Mars, where there's not.
An atmosphere too, though.
What's that?
Mars has an atmosphere too, though.
It does, and it's very weak, and it has a very variable magnetic field, and the propagation will be very different. I will just say as an aside, I mentioned that we were at ARRL headquarters, and one of the things that you see at the beginning of the headquarters is a little sort of cup. It's been there since the 1930s, the Elther Mathis Cup. It will be given to the first amateur that does a two-way radio contact to Mars. Two-way. You have to be on the surface and then come from Earth to Mars and back. Nobody's gotten it yet. Someday. The point is that we have a planet with an atmosphere that's rotating along with us, mostly, and it's well mixed at the ground, but then it begins to separate out by mass. It gets lighter and lighter and lighter as you go up in altitude. And altitude-wise, the space station is about here. So there's still an atmosphere quite a bit far out, even though it looks like the blackness of space behind the astronauts that are floating along. So, since we have a neutral atmosphere and we have all of these extreme ultraviolet photons, you end up getting an ionosphere out of it. And that's really very simple, because as these photons go into the atmosphere, you're using them up to ionize them. So the flux gets weaker and weaker and weaker, but the density that you're ionizing is getting more and more and more. So those curves cross and you get kind of a peak. That's called the F layer. And you'll notice there's the E layer. And I always tell this tale. E stands for electrified. How many people have seen the musical Cats? They talk about the Heaviside layer. Because this guy named Oliver Heaviside, who was a physicist, said, whoa, you know, signals are going beyond the horizon. There must be some kind of charge layer that's actually bending these over. And then later we have the F layer, which is one more letter than the E layer. Not kidding. And then there's the D layer, which is one less layer than E. This is what it looks like during the day, but it changes quite a bit at night. The E layer goes away, won't go into the chemistry, except for sporadic E, which excites people who like to go on 50 megahertz. Ah, Dennis.
Do the letters D, E, and F actually have a definition?
Yes, they have to do with something I'm going to put out in just 1 second. They have to do with their chemical composition. Yes. Because the chemistry determines how long they stay and how fast they get produced. Anybody? Sporadic E season, we're about in sporadic E season right about now, and so if you're up on 6 meters, occasionally for 15 minutes to a half an hour, suddenly you're actually going most of the way across the country, and then bang, it's gone.
10 meters as well. We had our 10-meter night,
Yep.
the 2-meter night the other night, and we had some nice sporadic E contacts. People were calling us from the Midwest, and yep.
And I can tell you that when I go to conferences, there are still a lot of papers on why sporadic E occurs, where it occurs. It's really tough to predict. So what you're experiencing in the radio is honestly borne out by just the medium itself. It's and there's a season. Most of it happens between April, May, and August. There's a little bump that occurs in December, much, much weaker. So
The peak in the end of June.
yeah, somewhere in that range, and it depends on year. Is actually very complicated. These are very thin, very sharp layers that are where the wind actually changes direction and piles up the ionization. Moves some of it up, moves some of it down, and you get this pancaking, very sharp layer. And that's kind of what can refract signals. And then the chemistry changes and bang, the layer goes away.
The longest sporadic E contact I had was from 2 meter simplex.
Yep.
From Detroit, Michigan to Naples, Florida.
That can happen. Here you are with your 144 megahertz radio figuring, you know, this is line of sight, local, and all of a sudden, whoa.
It was only a couple of years after I was new hams, and
It can surprise you. That's right. Somebody else had a question back there? Yeah.
Yeah, and when you try to describe those layers physically, do you try to find a relatively conductivity complex in real part or something like that?
Okay, so the layers are partially defined by the ions that go along with the electrons. And that composition changes as we go up in altitude because unlike the air that's mixed here at the ground, you know, if you grab a box of air, there's a standard atmosphere. Above this level, the air begins to sort itself out by mass. So you get heavier stuff down here, and then lighter stuff, and eventually it's all hydrogen and helium. The ionization is different at these levels, and that actually affects these shapes. So part of why we name this F or E, or the top side we call it, is due to that chemistry. The other reason that, and for example, at night you can actually have these sharp layers from little bits of meteoric dust that are burning up in the upper atmosphere and causing, you know, layers of ionization. But to your question about electric conductivity, these are charges and they're floating around, so there are sort of complex impedances that go along with this. And most of the conductivity is centered down here. There's still some conductivity up here, but that affects the electric fields that are floating around.
Yeah, but if you try to describe this by, say, epsilon times the tangent delta to get those numbers,
yes.
Are you going to do that?
You can do that in modeling, yes. You can actually look at the imaginary part and the real part of the impedance.
What is about the magnitude of the tangent delta of those?
See me afterwards. I'll talk to you about that later. I don't want to go that far down, but it's a good question. So, atmosphere is changing, things are getting lighter, lots of stuff happening, and then all of this is part of, not to scale. I don't think you want to live this close to the sun. That's, you know, a lot of million, 400. Well, let's just say the moon is 400,000 kilometers. This is about 150 million kilometers. And the sun is spewing off. It's the outer atmosphere of the sun is constantly evolving. That's something called the solar wind. And it's charged, so it runs into the magnetic field that surrounds the Earth. And so you get this teardrop shape, you get a tail, and then you get a front part called the magnetopause. And so this material starts interacting with these magnetic field lines, and they're all connected to the little ionosphere down here. And so there's a lot of electrodynamics going on. And so, you know, that's why I spend my career attempting to understand parts of this where I can. But as I mentioned, the ionosphere gets created, and I will just say, this is another view of it, showing you kind of the E region at about 100 kilometers and the F region at 200 to 300 kilometers, depending on time of day. And that it happens to vary, for example, from day to night. But this system is still horribly undersampled, even for professional networks. And that's kind of where HamSci is coming in. And just to show you what a model of the propagation is like, so look, this is what? 14.25 megahertz. This is in the middle of the 20-meter band. So let's launch some rays from a transmitter over here, and let's see what happens. The background is the ionospheric electron density that the sun is creating for us. And so you can watch the rays change, and you notice that the bounce altitude changed. Some arrays at higher elevations go right through and you don't see them again. But watch the skip distance change, all because of the background weather. So all the contacts you guys are making, look at the ray now. Look where its first bounce point is. We've now gone across the pond. At this particular time of night, this is about midnight in our sector, and the electron density has changed because we've gone from day to night. So the very propagation that you're using for HF waves going from here to there is directly dependent on that background, and it's honestly like a ray tracing exercise. Things are being bent and refracted. All right. So now I get into the HamSci updates. So some of you who have been following HamSci, the collective is trying to create something called a personal space weather station. The idea is there pieces of hardware that a technically inclined amateur could install at their QTH to try to take some data that is of a different kind than a professional network would take? And can we combine that with other professional tools that we have and begin to understand more about the system? Because one of the things we learn a lot about remote sensing is no one piece of data tells you the full picture. You need multiple pieces of data, each which have different things to tell you. The old analogy about the elephant, and you only see the trunk or you only see the foot, but if you collect all those experiences, you start understanding the system. It's called personal because the idea is eventually that these pieces, at the moment they're kind of separate systems, but eventually you have an aggregate. You should be able to purchase one, operate it in your backyard, upload the data to the internet, which we'll talk about in a minute, and then understand something about it. But if I told you, hey, can you now, say, buy an ICOM system, hook it up to this, you can't use it, and please don't touch it for 5 years. Okay, that's not as attractive. So we want systems that are either inexpensive enough or coexist with other things, or like I could say, here's a receiver, please don't transmit for the next 10 years. Not so great if you're a radio amateur. So it's an interesting challenge to try to do both of these things at the same time. But the collective has made a lot of advances, I think, in the last few years. So I'm going to go through some of them for you. So the first one, and in fact, there's a group called the New England Grape, which was started a few years ago, and that, for example, Bob, W1XP, has been very active in. It's essentially a system that records a narrowband signal at a couple of different HF frequencies and feeds it in, processes it with something called Whisper Daemon, which I'll talk about in a minute, and feeds it into a couple of different databases and visualizers. So the idea is from your location to try to understand how propagation is happening as you hear it from your location. And there's a nice little, URL there which you can find more about, but I'm going to give you a little bit of an overview here. This, for example, is sort of the simplest receiver. This is I mentioned the GRAPE system, and then this weak signal propagation reporter. Some of you may know Joe Taylor, K1JT. How many people here have used FT4 or FT8 to do transmissions? Okay. This is an unattended system designed to not tie up your transceiver because you're only receiving, but to listen for those particular transmissions and record them in a way that's scientifically useful and then upload them. You can see the components here. This is an RX888, which is essentially a commercially available little receiver. It's got a USB port and a sort of SMA port that you can hook an antenna to. This is something called a GPS disciplined oscillator, but made by a guy named Leo Bodner, who is a person in the UK. This is essentially to give you a precise frequency reference. So how many people here have tuned into WWV? Right? Almost some of the first thing you hear, because it's always there most times, after you get bored listening to the ticks and the time will be 01 hours, 36 minutes, coordinated universal time, beep. It's an AM transmission. What do we know about AM? 50% of the power is a constant carrier. And because it's coming from the National Institute of Standards and Technology, they lock it to triply redundant atomic clocks, which are actually synchronized to the NIST laboratory, which holds time and frequency for the United States. So you know what frequency it was when it left WWV, or WWVH, if you're on the West Coast. If you record what the frequency is locally, because you have a very good reference, then that Doppler shift, or that shift in frequency, tells you something about the ionosphere as that signal passed through the ionosphere. It's a very simple measurement. So that's why you need a local reference to give you a precise frequency reference, a little Linux mini PC. These are not very expensive these days. And I'll talk about some of the rest of this, and then sort of a little amplifier if you need it, and an antenna. But this is the kind of size of the system that actually is one of these little receivers. This is one of the setups we have. This, for anybody that has played with software-defined radio, this is an RX888 Mark II. This is essentially, again, a USB 3 device. It takes data in, and it's good enough that you can actually capture everything from a kilohertz to 64 megahertz. Anybody have a flex receiver here? You know that there are slices? There's no slice here. The slice is we're taking everything. If you run that with 16 bits of fidelity, anybody who knows analog to digital converters, that's pretty good, especially at HF. And you have a reference clock, and this is about $250. I don't want to tell you what that cost about 20 years ago when we were trying to put together a system for the big radar over there, but it wasn't any $250. So using the power of commercially available stuff, you can take that, feed in some reasonable antenna, and the antennas that people are using with this vary all over the place. Some people have dipoles, some people have vertical antennas. There's a wide variety of them. But if you can start hearing signals, you can do something interesting. And if anybody knows about amateur packet radio, that was actually pioneered by a guy named Phil Karn, KA9Q, who was actually a Qualcomm engineer. Phil got interested in being able to take that entire spectrum from 1 kilohertz all the way through to 64 megahertz and do something with it. And if you really wanted me to, I could send you the IEEE paper that talks about the calculations he did, but essentially he had figured out a way, and I'm not going to go through fast Fourier transforms and all that other stuff, but what he can do is take that and slice it up, essentially arbitrarily number. He, in fact, at one point used this to listen to every single 2-meter channel there was simultaneously. Each one was a little audio stream that he recorded at about 12 kilohertz bandwidth. This is something called multicast. If any of you know are computer hardware people, you know that the internet also supports local multicast, 1 packet to many. So if you do that, it's actually very cheap to add another channel, because all of the heavy lifting is done by that first calculation, and then you can kind of pick off little things. So you can kind of arbitrarily add channels here, and so your receiver starts to get more ears, more ears, more ears. Typically, these things run between 50 and 200 channels simultaneously. So it's kind of like having a flex with 200 slices. Rob Robinette, a person who's been working a lot with this, and a UK guy, Gwyn Griffiths, who has the nice distinction of being somebody who was awarded the Order of the British Empire by the Queen. He had a career in meteorology, and when he retired, he got interested in this. So between Rob and Gwyn and a couple other people, there's a complete downloadable package there that is being used in this particular system that will set up this multi-channel thing with a nice little configuration file, and you start running, and you start feeding that into data like PSK Reporter. I'm looking at you, Phil. That's Phil Gladstone over there. That's the guy that started PSK Reporter, by the way. Thank you very much. There's billions of spots now that are in the PSK Reporter database that are also being used for science.
For all the new people, can you quickly explain PSK Reporter
Yes.
and how this works?
Sure. So you remember that some people talked about people using FT8 or FT4 or even some other coding modes, that this guy named Joe Taylor, who, of course, also happens to have the Nobel Prize in 1974 for discovering binary pulsars at Arecibo, but we digress. These are very, very narrow band communication signals. So if I had an HF receiver here and I tuned it to 14.074 megahertz, you'd hear a really weird sort of sound that are 20, 30 people all transmitting these little codes that are very narrow transmissions. And it turns out that they go surprisingly far, sometimes farther than our theories predict. Well, if you're sitting there, you can simultaneously download every 15 to 30 seconds, depending on the mode, 20, 30, 40 of these transmissions that are coming into you. And then if you upload them to Phil's server with a nice particular protocol, which is all built into things like FT8, or into this Whisper Daemon, you start to notice trends, and I'll show you about that in a minute. And so this is a way for people who like to do digital work, which is transmitting short messages that say, you know, W1PJE, you know, KA9Q, W1PJE, signal report 73. These are very short things, but they are, for low powers, they go quite a long distance. So it's something very interesting to learn about. ARRL has a bunch of information on how to set up your transceiver for doing that. Maybe that might be something that we could do in a future sort of exercise if we're setting up a station. It's all done in an audio bandwidth, which means it works with a wide variety of transceivers. And so there are literally, if you tune across the bands now, there are these little 3 kilohertz slices that are just filled with signals. They're there all the time, pretty much, every time I've looked. And so all of that data gets vacuumed up now by things like Phil's server, and then it's available for those of us who have pointy hats, who would like to do collaborative citizen science. This just happens to be a very nice software package which has made that sort of setup a little less manual and a little easier. So what can you do by just listening to these things? We're not even transmitting right now, we're just listening. Whisper, by the way, is something called Weak Signal Propagation Reporter. That's an even longer code. That cycles once every 2 minutes as opposed to every 15 seconds. And you can't transmit very much information, but its detectability is even farther down into the noise. Sometimes when you tune into a whisper, you can't hear it. It's 20, 30 dB, 3 or 4 S units below the noise floor. But you can decode it if you know what the pattern is. So this has really been a revolution, and I can say that this started in the last solar cycle when it was solar minimum and propagation was not so hot. And people discovered that with a very small system in these coding modes, you could start actually making contacts quite a bit farther than you would if I had to always have a 500-watt Aurora Flex Radio, HF amplifier, for example. So we can take advantage of this data. One of the nice things that comes along with this data is that one of these little slices out of the 200 that are sitting there just listening away is controllable with a nice waterfall display. So you have a nice little waterfall display, and you can kind of pick what frequency you're listening to, and is it an AM signal, is it a single sideband signal, and you could actually sort of listen to regular communications all at the same time when this system is sitting there recording all this other data. And I run one of these at my house. The dots, thanks to Phil, are all the stations that I heard in the 12 hours since I pulled that. And I'll show you the antenna in a minute. There's Japan, there's Europe, Africa, South America, US. This was listening to all FT8, FT4, WWV, CHU, and whisper frequencies at the same time. And I do nothing. I just sit there. And every so often, it records them and uploads them. This list is it's all the whisper stations, the really weak ones I heard, in only a 4-minute interval. So there's a lot of data that comes in on this stuff. Now I'm going to show you what the antenna looks like. That's the antenna. Floppy. Anybody? This is an MLA 30 plus. This is a loop that's about $30 on Amazon with a little cable and a little low noise amplifier. That's the thing that was generating all that data. You can see how powerful this is. And this came out this morning, so I thought I would, show you the fact that we have very nice heirloom lilies that I haven't managed to kill yet. It's spring. So this data is going along, and again, it's happening alongside your regular FT8, FT4 communications if you happen to check the box, which is checked on by default. So even if you're not using the whisper system, but you're actually doing transmission, that data also gets fed into this particular database. The whisper daemon is just a very nice compact package to be able to do that if you only want to do receive. And that's just a receive-only antenna, by the way. That's not a transmit antenna. And believe me, its manufacturing is commensurate with its price. If you look at it sideways, you're like, that's going to fall over. Anybody familiar with the call sign K3LR? That's Tim Duffy. Tim Duffy has a superstation. You will see pictures of the superstation later.
He gave us a presentation here.
That's right, remotely, right? I believe?
Yes.
So Tim has been developing with a bunch of people also a contesting dashboard. Can we take this data and turn it into something that a contester could use? For example, where are the spots from where you are to where you'd like to go, maybe that are tuned to a particular contest that's going on? So there's some more work going on to try to put a front end on this that might be useful for people who are actually, want to go on the hobby and do what we're all here to do, so what we get licensed for, but at the same time, have some data going into a scientific database. So I'm just going to show you a little bit I mentioned that the simplest thing you can do is listen to the National Institute of Standards and Technology, which has a frequency, for example, locked at exactly 5 megahertz, or exactly 10, or 15, or 20, or 2.5, or 25, or CHU at 3.33 megahertz, and 7.85, and 14.85 megahertz, because the Canadians have to do, they've been there as long as WWV has. And has anybody listened to CHU here? Yes. You know what happened? You notice at the end of the transmission, they read it in both English and French, and you notice that every other minute they switch which goes first. It's French and English. and then it's English and French. Because we have Quebecois, and we have, you know, the people who live in Ontario. So that's a carrier. So you can listen to that. So again, whether this is WWV or CHU up in Ottawa, as the path length decreases or increases, because the ionosphere, for example, might be moving up or down. Anybody remember the fire engine? You know, the fire engine comes towards you, and the frequency goes up, and then it goes away from you, and the frequency goes down. As the path length gets longer, the frequency goes down. As the path length gets shorter, because the ionosphere drops, the frequency goes up. And that little movement is something you can sense. And for example, this is a little plot. Now this is zoomed in. This is only about 5 hertz plus or minus from a 10 megahertz transmission. So you're not going to be able to hear that, okay, even if you turned on your CW mode on your transmitter. But you see all this fuzziness here and all of these wiggles. Those are traveling waves in the upper atmosphere. And this particular one was taken during, is this date familiar to anybody? Anybody see the eclipse that went up the East Coast a couple of years ago? This is when the eclipse happened, right there. And basically, for a brief period of time, we had night, and then it turned into day again, very fast compared to what a normal day to night or night to day transmission means, which means that the ionosphere didn't have time to cool down before it got heated up again. So weird kind of physics happens. This is the 5 megahertz WWV, 10, 15, and 20 as a function of a full day. And you can see that not all the frequencies behaved the same. In particular, you know, 5 megahertz went out for a little while, and then 10 megahertz kind of did something different. And look at this. See that? That's the ionosphere cooling and dropping and then going back up again. So just by listening to these frequencies and recording what frequency you heard, you can actually start trying to figure out with a model what's going on. So I've just described where we are. Where we're going in the future are feed in a pulse per second so that we know precisely to a tiny fraction of a second, like a couple of nanoseconds when the data was actually taken. So then you can combine it coherently with other data and you can make different kinds of products. This is the RX-888. You don't know how long that's going to be produced because we're not producing it. It is just part of the ecosystem. So there's some hope that the TAPR people, that's the Tucson Amateur Packet Radio, who make a lot of interesting gear for hams who are trying to do this kind of work, may be making their own receiver. And maybe extend this up to 64 megahertz full. A lot of times you sample only to 32 for some of these things just due to data. So being able to do everything it's up to 2 meters, 6 meters, excuse me, all the time would be very good for, we mentioned sporadic E, or meteor scatter. We've talked, I think some people have tried meteor scatter in this club. Exactly. Talk about short bursts. That's the meteor coming through the atmosphere and leaving a little ionized trail that lasts for some couple of seconds or 3 seconds, and then the trail disappears and then another one shows up somewhere. So little bursty communications. Okay, so I've just talked about something which has got one end of it that, you know, the National Bureau of Standards, or NIST, spends a good amount of money keeping running. Wouldn't it be nice if we had the ability to do some lower cost version of a beacon that would do the same thing? Well, this is the Whispersond. This is a GPS disciplined 8-band beacon transmitter. That's about how big it is. It's locked to the GPS cluster so that it maintains absolute time, and 2 amps at 12 volts. And the idea is that there's a passive antenna splitter, so if you really wanted to, you could hook that up to an antenna and share the antenna with something else that was receive only. It's a little hard to share that with something where Les is pushing the button and a kilowatt is going out the antenna. This is probably not going to like that very much. So there's some work on actually doing that. So far I've talked about HF, right? Where things can go long distances. But another thing you have to understand is very low frequencies. And for those of you who are new to the club, you may be able to go to YouTube and see a talk I gave here about a couple of years ago or something like that about VLF. That's very low frequencies. So low that the entire the space between the surface of the Earth and the bottom of the ionosphere at about 100 kilometers is a giant waveguide. And things go very far. That's why submarines use it for one-way communications that even penetrates into seawater. There's a lot of natural phenomenon. That's what my talk was, in fact, showing you, that actually happen at those very, very low frequencies. How low? We're talking like 20 kilohertz, almost at the top end of the hearing band, but they're not acoustic waves. They're still electromagnetic radiation. There's stuff that happens even lower than that. So the idea is to try to add to the Personal Space Weather Station 4 locations that are conducive to this. You're not going to put that out where the cars are driving along, okay, where you're going to get a lot of magnetic fields. But can you have an active antenna that actually listens to sort of transmissions that nature is putting together in the Sun-Earth system, and listen to currents that are flowing along in this very, very complicated electromagnetic sort of puzzle that is being fed from the sun, from the solar wind and other energy, and there's circulating currents. There's something called the ring current, and here we are down here, and a lot of that couples down to these very low frequencies that one can actually hear. So there's some work to be able to get a receiver down at that point. There's also work to get a magnetometer, because when currents flow, anybody remember your right-hand rule from physics? Or maybe you didn't ever wanted to have a physics course again after you saw that in high school. But when a current is flowing, there's a magnetic field that's kind of like the curling of your fingers. So if there's currents flowing overhead, there's actually magnetic signatures that you can detect from the ground. You put those together in networks, you can start figuring out what the electrodynamics of the ionosphere are doing. Nowadays, magnetometers have dropped in price, and so that literally is a magnetometer. And this is science grade for $100. Put it in a PVC pipe with some insulation, and you can, very tiny board, it's about that big. And that's because this is a flux gate magnetometer. And why do we have cheap magnetometers? There's a magnetometer in your phone. You can actually get an app, because they want to know what orientation your phone is, so that they can tell whether you're doing this or you're doing that. So there's millions and millions and millions of really cheap chips that if you drive them the right way, you can actually turn into a science instrument. So that's part of what's being added. And all of this data, whether it was HF, whether it was VLF, whether it was magnetometer, is going into a database at the University of Alabama. Those are particular nodes now for these are people who have put together pieces of the Personal Space Weather Station. You can see it's getting off the ground, but we don't really have yet a kit that one can just buy and construct. A few more years to develop that. But you can see that the pieces, I guess, are beginning to come together, which was quite a difference than when I first talked about this stuff at HamSci in this club, where literally we were just beginning to feel around what was possible. So a lot has happened in a few years, actually. That's just the deployment. A lot of this is individuals spending their own money, so this isn't necessarily a grant. The grant is to actually run the server that collects the data, and with help from people like Phil, who have already been collecting this data for a long time, and get it on a time grid and to the point where one can do science with it. And I could list a whole bunch of papers that have come out using this kind of stuff, but trust me that there's more coming. So just finally, what does installing and operating one of these little Personal Space Weather Station HF receivers look like, for example, and a magnetometer? So this is a place called Jenny Jump, New Jersey, and if you looked at this QST article, there's a nice one that talks about what I'm going to tell you in a minute, which is how does one install one of these stations. So this is down at, it's not that far from, it's in the dark part of New Jersey that's within access in the Jersey Institute of Technology, which is near Rutgers. And so here's Nathaniel with students. Hey. Students, and you can see a couple of towers in the background. And this was one of the PSW installation at Tim Duffy's superstation at K3LR. Because we know Tim, for example, is a good test site because he's got transmitters. Can this thing coexist with transmitters? And he's got good bandwidth. So he can easily upload data for us. So if you haven't seen videos of Tim's station, and I know there was a presentation, but wow. So Tim has a lot of infrastructure and very good and patient neighbors too.
So if you just look, the tower on the left My guess it's 180 feet tall.
Yep.
or that
Notice it
kind of
has to have a light. Yep.
And each cross piece you see going down is separate antennas that are on the tower. But he has, in this picture, I can see at least 3 towers, but I think he has a lot more than 3 or 4 towers.
Yeah, there's a fourth one.
Yep, and that's just looking in one direction. If I turned like this, there's more towers in the other direction. He's very nice to his neighbors.
They're used to it.
They are. So, a lot of the antennas that people have been using with the station are basically active verticals, because with a low noise amplifier you can actually resonate. You know, they can work on a bunch of different bands. You don't have to cut a separate vertical, which is a quarter wave typically for every band that you want to use. So here's some of the students installing it and running cable back to the central location, and here's the students, you know, using a power auger to drill a hole in the ground for the magnetometer, and there's the magnetometer going in, the finest PVC pipe from Home Depot or Lowe's, if you prefer Lowe's, to put the magnetometer in, which is nice and water sealed. And there you can see the vertical antenna, the base of it here, and then there's the magnetometer pipe, kind of put away from the house where there's a lot of flowing currents from the AC power lines. And this is the Whisper Demon receiver in operation at Tim's station at K3LR. There's the data coming in, and it's at the time being uploaded to the servers that I mentioned before. This was back in October. So that station has been running continuously for going on close to the year. And the nice thing was that when they were installing this, they got to get a tour of K3LR. And again, because there's some of the more towers, Tim has talked about this, but I like this wide field shot. That's all the awards on the wall. And there are more on this wall and that wall. Tim is like one of the top 2 or 3 stations in any contest usually. There's a couple of other contests that they try to go back and forth on, but this is an amazing kind of installation. This is more young people actually using Tim's station to make contacts. He has separate dual stations on every band for contesting, and it's just nice to see students and younger Ham Club members doing that. And then this is the installation team at K3LR. There's Nathaniel and a few other people who were instrumental in getting that station installed, and it's running today. And if I pulled up a web page and did the right kind of sorting, you can see Tim's data rolling in on all bands. So that's where HamSci is now. You can see that it's evolved quite a bit, and there are HamSci presentations at every major scientific conference: American Geophysical Union, the CEDAR meeting, the GEM meeting, the SHINE meeting that does solar physics, the International Radio Science Union that happens in January. I've seen presentations on this kind of technology and results at all of them. This is like a boulder that's now rolling down a hill, and there's no stopping Nathaniel, and it really is quite a community heavy lift. It's been very successful, and I can tell you that federal funding people have noticed this. This gets a lot. This is one of the premier citizen science sort of efforts kind of anywhere in the United States right now. And it's got some international components. I think you've been asking questions a little bit along, but, you know, and I'll be around. So really, hamsci.org is the place to go. Yes?
You're gathering, everyone's gathering this incredible amount of data. What's the end goal?
Yes. Okay. The end goal, right.
Well, yeah, I mean, it's cool, the data's cool.
Right, of course. I mean, if you collect data and you don't do anything with it, there's not much point to it, right? So in addition to providing some more like visualizations for people who are like, for example, hams who are doing their hobby work and would like to know something about maybe what bands you might want to use, and alongside some of the tools that are already available like PSK Reporter, like Whisper.rocks, and a couple of other things. What we're discovering is that at the beginning of this, I showed you this big telephone book, which was the community's decisions about what we need to study for the next 10 years. The word that comes up again and again is something called mesoscale. That scales between about 1 kilometer and 100 kilometers in the upper atmosphere. 110 kilometers is about 1 degree in latitude or longitude. So if you think about a grid square, this is stuff that's pretty fine sub-grid scale. We know so little about that physics that people don't even understand how to construct models yet of it so that they can actually figure out where they don't agree with the data. They're very data starved. Having lower cost, limited systems, but in a much broader sort of distribution is the way that we can actually begin to construct that kind of physics models, and you'd be surprised how much that actually drives dynamics in this whole system. It's not just the big stuff, it's actually the small stuff and the even smaller stuff. And we've already noticed that because if you look at propagation trends in this particular data, you will find out that anybody familiar here with VOA CAP, that's this Voice of America program that was developed by the shortwave broadcaster Voice of America to figure out where to reach their consumers on shortwave when shortwave was still a thing. You can take a contact that was made on one of these digital modes that is part of this system, and then you can go and run VOA CAP, and I can show you a lot of paths that should not exist, but they do. So there's some piece of physics that we don't quite understand yet that is concentrated on those smaller scales. It complements all the professional stuff that we've been able to do, which is not infinitely funded and is limited. So by synthesizing them together, you get a picture that's greater than just the individual elements. So that's really the goal of collecting all this data, is to be able to look at some of the statistics of where these little wiggles are and why they're there. Because the system is complicated.
Has the latest advances in AI, have you started to integrate that with
He used the word artificial intelligence or machine learning. Yes, there are large efforts in the last 2 or 3 years to try to make a lot of data sets like this one AI ready, to have an interface that's friendly enough that someone can vacuum up large chunks of data. So that's also underway. I will tell you that AI knows as much as the training set that went into it. And if anybody's played with AI, it can give you very confident but yet wrong answers, which you as the human have to say, I don't want to see any more of those, okay? That's either wrong or I know about that already. Show me the things that you find that are interesting in this vast data space that maybe I want to tell you to find more of those. And then you start building a physical picture. So yeah, this is not going to happen without the heavy lift of having those tools, but it's still human in the loop. It's still physics people who understand what looks right and what doesn't look right and what is, wow, I don't understand that at all. Let me find some more of that. So yes.
Thanks.
Yes.
Given the volume of data you're talking about, where and how are you storing it? Because it seems like this is something that's going to grow
Yes.
immensely quick, and you only have so much space, and adding space is expensive.
It is.
Especially now.
So there's 2 answers to that, I think. The first answer is I mentioned the dedicated server that's funded under the National Science Foundation to try to derive enough space to collect that. And for the second answer, I'm going to punt to the expert in the room that's sitting right over there. Phil, what would you say about the growth in data you're ingesting and how you're trying to deal with it?
This is actually a very good question because we are in the process of moving PSK Reporter to not just be supported by me, but we now have a 501c3 sponsor, so we will be taking donations, and we are rebuilding the infrastructure to store vastly more data. I mean, we have under 100 billion records at the moment, which is not very many.
Right.
And we're looking to increase our ingest rate by at least 1 or if not 2 orders of magnitude.
Right. And if you go to Phil's site, at one point, I'm sure it's still there was a little counter that showed you how many records are coming in as a function of time. I recommend you stare at that for about a minute and understand that this man was doing this honestly on hardware you were supporting in your basement.
In my basement.
Yes.
Yes.
And so we are riding on the shoulders of people like Phil, who have started the ball rolling that we can all understand how valuable that data is and then try to get some more support, like you were saying, to actually make this real. It's walking into the same problem that all of these large data sets are, which is they're growing faster than the cost of the storage media to contain them, or the other way around. And yeah, we're going to run into some interesting problems.
How big is the record?
Record is not that big. Depends on what you mean.
It's huge because of the indexes that get built in the database.
Yeah.
So we're going to move from using MySQL to probably something like ClickHouse, which is designed for time sequence data, where you can get much more efficiency.
Right.
Like
So
probably two or
less overhead for the data itself.
There's the data, but there's the metadata, which is the stuff that actually makes the logical sense, that allows you to quickly bundle it. And that is actually, if you're not careful,
Yeah,
that will grow like this. I mean, that is really tricky to get right.
I mean, okay, it's 200 gigs a week.
Now, but naively you can say, well, I can go to, Best Buy and buy a 4 terabyte hard drive. Yeah, that's one hard drive. And by the way, don't try to go buy that hard drive, because in the last 4 months, everything has quintupled in price, because the AI data centers are vacuuming up all the computer hardware in the United States at the moment. But never mind that. You can't just have one drive with that's single point of failure. You have to have multiple copies of it. You have to pay for bandwidth coming in. You have to pay for bandwidth going out. There's a lot of sort of heavy lifting, if you will, in keeping this going, as honestly, it's a community facility. That's exactly what it is. It's just that it isn't funded in the conventional way that a community facility is funded. It is grassroots.
So is the data replicated across sites so that if one goes down, it's
It's good enough.
maybe.
So the people have, there is a big database run, I don't know whether it's run by you guys, the Madrigal system.
Yes, that's run right over there. Yep.
Which in goodness knows what they store it on, but they have actual funding.
We do.
As opposed to me, when I have nothing.
I can tell you just very briefly about that. If you have a facility like a data storage facility, and you are in fact the long-term archive for the community, I might need to do for example, I might have data that goes back 5 solar cycles, and I want to be able to retrieve it, because if I'm looking for climate, right? That means I need 3 copies of it in 3 different physical locations, not just the one I have. And I have to pay somebody for those other 2 sites. And if anybody knows anything about running things on a cloud, what you find out is they'll give you CPU cycles. They don't want the data hanging around. They want the data to come in, calculate, and get out. If you say, oh, well, I'd like to keep all this stuff around and it's going to get bigger and bigger, either the price goes like that, or they kind of just don't want to talk to you anymore. So this is another one of the edge cases that the community has to develop. But it's nice to push the envelope, if you will, so that actually there are good questions like that one to try to answer. So it's actually part of the research project, really.
I have a 16 terabyte Synology space in my lab at home. I can only imagine how long it might last.
Yeah, but there's, as the network gets more dense, the problem or the challenge compounds. Any other questions about this particular material? Great.